Alright, squad. Welcome back to 49, so strength conditioning. Those of you that weren't here on Tuesday, feel free to hit me up after class if you guys have a question. Quick recap for those of you that were here. Again, so we'll have quizzes on every chapter of the CSCS prep textbook, so Essentials of Strength and Conditioning. So we're going to cover chapter 1 today. This is the intro, basically, to the whole course. Today's really, honestly, it's going to be like an anatomy review. The content is going to be a little bit more dry, so to be honest, today you're going to hear me talking kind of off the slides a bit more. This should be a review. I'll work with you guys to kind of talk through this and talk through some of the content, maybe give analogies, etc. But today, Thursday, Tuesday, Thursday, etc. Kind of expect for a lot of it to be review. Review on biomechanics, review on anatomy, review on bioenergetics and metabolism, etc. Until we really start getting into new content in a couple weeks. Okay. Quick rundown on class. So today we're covering structure, function, body systems. Okay, both macro and micro level. And then you guys will have a quiz due on this content on Tuesday. Okay, quiz due again on Tuesday. 10-question quiz, should be pretty minor. Okay, should be all good. Just make sure, honestly, read the textbook with the slide deck. Plus, I'll be posting this on YouTube afterwards. We should be really pretty good, pretty set to go. Okay, cool. All right, let's go ahead and get started. So, chapter objectives: macrostructure, microstructure of both muscle and bone. Again, this is really going to be a central review of anatomy, some base phys, going over the sliding filament theory, physiological characteristics of different fiber types, so type 2X, type 2A, and then type 1, right? And then we'll go through some stuff of cardiorespiratory system, respiratory system, etc. What I think is important for you guys to know, like a question that I've seen commonly on the CSCS is like, explain the blood flow through the heart, if that makes sense. So which atrium does it start in, right or left? Which ventricle does it eventually pump out of, left or right? Does that make sense? So think about, we're just doing this as a review to go through which atrium does kind of like blood flow, venous blood flow return to, and then which ventricle does it pump out of. That's kind of the scope of what we'll be covering today. Okay. So the skeletal system, I didn't remember this until I reread this slide deck. We have 206 bones in the body. I confidently told my fiance there are 208. She said BS, and so I had to buy her drinks a couple of days ago. But 206 bones in the body. What's important to know about the bone structure, it provides leverage. Okay, leverage. When we say leverage, when we're talking about muscles, it's really important to note that muscles pull. That's really all that they do, right? The movement might be some sort of pushing pattern, but muscles create tension and pull on an end. So there's an insertion point, right? There's an origin and insertion, and really all that muscles do is they contract and create tension, and they pull. So when it's saying that the skeletal muscle provides leverage, what is that implying? It's something to anchor and pull to create movement. You guys with me there? It's providing the leverage to be able to create tension and induce movement. There's support, so obviously we have structural support. We wouldn't be able to stand very well if we didn't have bones. And then protection, think protection like sternum, rib cage, etc. And again, just quick recap. Basically, skeletal muscle, or the skeletal system is pulled on by muscles to allow the body to push or pull. Right? So it's kind of like a misnomer. Muscles really just contract and pull, but based on where the origin and insertion of the muscle is, it can express itself, that contraction can express itself as a pushing movement or as a pulling movement. Okay? Questions on that? Pretty simple, yeah. So again, this is going to be really base level anatomy. Okay? So we'll have the front view and the rear view, adult male. I think to go over this, we're going to do this real quick. So I'm going to point to a bone, and you guys are just going to verbalize what that is. We're going to go through this really quick, okay? So these two bones, clavicle, good. We have, let's see, what would be the next one here? Sternum, ribs, okay? I have a certain spine right here vertebrae, cervical spine, and then you have your thoracic spine, and then the bottom of that, lumbar spine. Good. We'll shift to the arm. What's the upper bone? Humerus. Some of you guys are sus on that one. Okay. Then we're just getting into the wrist, right? What are the bones called inside of the wrist? Okay, good. And then fingers, phalanges, however you want to break it down. Okay, going into the hip girdle, the big thigh bone is femur, and then we've got two, tib, fib, right? And then the ankle complex, and then the ankle. Okay, if you have that down, you'll be fine. Oh, I missed the kneecap. What's the scientific term for the kneecap? Patella. Silky smooth. Okay, we're all good. I don't think you guys need to spend time studying that, but we covered it. Okay, all good. Why do we need to know this as strength coaches? Because it's all about context and conversation, right? If you have these things dialed in, we can have in-depth conversations about where people are feeling pain, or what site we're loading, or where something might be bruised, or when an athletic trainer is telling you there's some sort of injury, etc. You're on the same page, and you can communicate those things pretty well. Okay. All right. What's the difference between axial and appendicular? Okay. Axial and appendicular. Bottom line, axial is basically the center part of your spine and your head, everything that's central. Okay. What's the easiest way to remember what is axial? You guys heard of the term axial loading? Axial loading. So for example, in children, there's a debate that children should not participate in axial loading exercises. So what is that implying? Children should not put a really heavy bar or weight on what part of their body? On their spine, on their back, potentially compressing their disc, etc. Right? There's a lot of debate around that. I'm not saying that kids should or shouldn't lift, but what I'm saying is that if you hear someone say, oh, let's avoid axial loading, they're saying let's avoid that. So give me an example of a movement with a barbell that is an axial loaded movement. Barbell back squat, right? Really simple, you have a bar in your back, it is an axial loaded movement. Whereas in contrast, what's another movement that is not axial loaded? One louder, someone? Bench press, thank you, bench press. Bench press is not an axial loaded movement, okay? We all get on the difference, axial. Appendicular is like everything else other than the axial zone, okay? Your arms, legs, etc. Okay. All right. Types of joints. Again, we're going really basic to start. It's probably a good way to kick off the semester. But if we break down types of joints, basically a joint is a junction of bone. We've got fibrous, cartilaginous, and synovial joints. So a fibrous joint allows virtually no movement. So example of a fibrous joint could be sutures of the skull, right? Basically don't really move. That's it for that one. That's pretty simple. Yeah. Cartilaginous joint allows limited movement, very limited movement. Think intervertebral disc, etc. And then a synovial joint allow considerable movement. Example: elbows and knees. Synovial is an important key word here because that implies that what component is inside of those joints? Synovial fluid, right? So that immediately makes you think like kind of like bursa sacs, etc. Right? You think shoulder, elbow, things like that. Okay, all good on this? Okay. Joints move in essentially different planes. So if a joint is uniaxial, it moves along what axis? A single axis, multiple axes, etc. Just think Greek roots, right? The uni, it's one axial, one axis. That makes sense? It can be in the X, Y, maybe the Z plane, but it's really gonna operate as a hinge. However, is that kind of a misnomer? So for example, does the elbow only really move in one axis as a hinge joint? Does the joint really only move in one axis? Yeah, but is there slight variations of maybe movements within that context? Does that make sense? This is a generalization, but we're basically saying that a hinge, the elbow and the knee, our hinge joints, they really just move in one way, right? But there is small amounts of movements that can happen in different axes. We're just generalizing to say and grouping this joint's function into kind of one term. Okay? Biaxial can operate in two perpendicular axes. Good example is the ankle and wrist. Okay? Ankle and wrist can go in deviation, flexion, extension, essentially, right? And then last but not least, multi-axial. Think ball and socket joint, think shoulder, think hip, etc. It can move in multiple axes. Okay. All still pretty simple, yeah? We're good? Questions or anything? Okay. Hopefully this is just a quick recap. Vertebral column, we kind of already hit this, but we have cervical spine, thoracic spine, lumbar spine, and then I kind of group the sacrovertebrae and the coccygeal vertebrae as one, just as kind of like the pelvis. Why? Because they're mostly fused. So from like a corrective exercise standpoint, from a like where can we improve someone's mobility, lumbar spine, thoracic spine, cervical spine, etc. Those bottom two kind of end up getting grouped together because they're kind of locked in a way as a unit. Okay, kind of locked as a unit. But regardless, I think we just need to, I don't know if for the CSCS you need to memorize how many are in each, but it's 7, 12, 5, 5, and essentially 5. Okay, 7, 12, 5, 5, 5. Easy way to break that down. Okay, so 7 cervical, 12 thoracic, 5 lumbar, and 5, 5 below. Cool. Questions on this? I know I'm kind of flying through this, but hopefully at this point in your career should be a quick review on all this. Okay? So the muscular system, we're going to look at macrostructure and microstructure. So we're going to look big and we're going to look small. So when we're thinking big, what does that mean macro? Let's say the thigh. The thigh is a group of muscles, right? The quad, there's really 4 major muscles within the muscle. And then we're going to take that and go into each muscle, essentially, or each group of muscles, and all the way down to what's called the sarcomere, which is the smallest contractile unit of muscle. So we'll start really big, and we're going to zoom in. But what is important to know is that each muscle is actually considered an organ. Okay? Muscles are organs. Sometimes it's kind of like a misnomer. There's sometimes a disconnect between health and like muscle physiology, because muscles are organs, which means they have the capacity to induce systemic physiological changes. What that means is when you exercise, if you think about the muscle like an organ, does it have the capacity to release hormones into the body? Does it have the capacity to interact and change how we're functioning and our current status is? Does that make sense? So try not to think of muscle just as muscle, but kind of like, I'm not saying muscle is a kidney, but are you guys with me? It has the ability to release chemicals that change our physiological status, our state, okay? And then it's really important to note that muscles are surrounded by a fibrous tissue, connective tissue, okay? Basically an epimysium, and it covers all muscles in the body. I think there's around 430, yeah, 430, well, I remember. So there's around 430 muscles in the body, but they're all covered by connective tissue. What's important to know, and if you guys want to take a deeper dive, is that there's a concept or systematic approach to looking at our anatomy called anatomy trains. And basically, it implies that all things are connected, right? All muscles are connected to each other, okay? How are they connected to each other? Is because they're all wrapped in this fibrous, elasticy tissue that's kind of like saran wrap in a way. That makes sense? It's kind of like saran wrap. It goes around the muscle. It also goes around where the muscle attaches and becomes connective tissue as well, okay? But that's all connected. So when you pull on something, like if you pull a hamstring, if you injure the hamstring, right, that has complications that occur upstream and downstream because the connective tissue is all one systematic process. It's one group of things that work together. Does that make sense? So if you think about like the posterior chain, you have your foot, the arch of your foot becomes the Achilles, which becomes the calf, which then actually, if you look at anatomy trains, becomes the hamstring. that comes up through the groin, becomes the lower abdomen, kind of like psoas tissue, and it connects all the way up. So when you hear someone say something like, I have low back pain, right? Well, the reason I'm sharing all this is we want to really think macro structure as well. We don't just want to isolate and try to do things for their back, because mobilizing or maybe releasing tension with a trigger point in their hamstring can reduce the low back pain, if that makes sense. Why? Because it could all be connected depending on the context. You guys are with me? Okay? It's all about context, but we want to think big picture because it all really is connected. All right, so we're going to take a look at a muscle fiber at a big picture level and small level, but 3 key Greek words: epi, peri, endo. So epi, outer layer; peri, surrounding each fasciculus or group of fibers; endo, surrounding each individual fiber. I want you guys to think of, or consider thinking of muscle like if you have a straw, you have a single straw, that could be a single muscle fiber. If you have a group of straws with one rubber band around the group of straws, that can be a fasciculus or group of fibers. And then if you have a bunch of straws with rubber bands, like packs if you guys are with me, so you have one straw, and we have a bunch of straws all together, held together. And then now we're gonna take saran wrap, we're gonna have like 50 of these little fasciculuses, these little packs of straws, and we're gonna saran wrap all of them together. That's a muscle fiber. One big, like that's a quad, etc. You guys with me there? Makes sense? So we're looking at micro level, one fiber, group them together with a rubber band. That's a fasciculus, basically, a group of fibers. And then if you have a bunch of those that are held together by rubber bands, if we saran wrap all of them with connective tissue, now that's one big muscle group, so to say. Okay? All right. So let's start on the small end. The smallest component of a muscle is actin and myosin. Actin is thin, myosin is thin. I'll tell you guys right now, you just have to know those. Those two terms, I guarantee, will come up to some extent on a CSCS exam. Want to make sure we have these myofilaments. These are basically the smallest myofilaments, the smallest size, the smallest things of muscle that we talk about are actin and myosin. Okay? A myofibril is basically a group of those myofilaments together. Okay? We've got a sarcoplasm, sarcolemma, which is the connective tissue around. We've got nucleus, right? We know that muscle cells are multinucleated. There's lots of nucleus all over. That's so that way we can duplicate those nuclei. Okay? And then we can cause systemic things to change with satellite cells. This then is considered a single muscle fiber. So one muscle fiber composed of each of these entities. If we group those single muscle fibers together, right, wrapped with endomysium, it becomes a fasciculus. We see that if it's one straw, we put all the straws together, a rubber band around all of them. Then we're here. At this point, we have a bunch of those things of straws. We take them, we saran wrap all of them with epimysium, right? Saran wrap. That becomes a muscle cell. And then that saran wrap also becomes part of the tendon. Okay? All connected. All good with that one? Questions? It's all review, yeah? Okay. Okay, a motor unit. What do we need to know about a motor unit? I think most importantly, we need to know that motor units innervate specific muscle types, okay? So we've talked about type 1, type 2A, type 2X fibers. A motor unit will only innervate the muscle fiber type, a specific muscle fiber type. So a motor unit will not recruit type 2X fibers and type 1 fibers, okay? It will only innervate the specific muscle fiber types that it is connected to, so to say, okay? But a motor unit is a motor neuron and the muscles that it innervates, okay? Motor neuron and the muscle fibers that it innervates. So there's typically several hundred muscle fibers in a single motor unit. And these differ based on the task at hand. So for example, let's think about the movements of the eye. Are the movements of the eye really fine movements? Are they big, kind of powerful, need a lot of muscle to do the movement? That question makes sense? The eye is really fine, right? So if we have one motor unit for the entire eye in each way that it turns, could you imagine trying to like focus on things if your eye was like every time it contracted? Makes sense? So in that sense, does it make sense for fine motor movements that we have a large amount of motor units? That makes sense? Fine motor skills, we need more motor units. Why? Because we want to very easily control the fine motor skill. Does that mean there? Does that make sense? Okay. Whereas in something like extending the thigh, forcefully, a type 2X fiber, forcefully extending the thigh, would it be more beneficial to have one motor unit, well many, but let's just generalize and say one motor unit that you recruit that kicks out your thigh really forcefully and activates all the muscle fibers for that, right? So it's purpose specific. So remember, it's all about context. Motor units are specific to the movement that is required of that specific tissue group. Okay. Okay. Quick recap. Dendrites. Dendrites are basically like the branching roots of the nucleus, I guess, in a way. We have the axon. Nodes are pretty near, if we remember. Those are so that way we can send electrical signals. They kind of jump the gaps a bit more efficiently. Myelin sheath also increases the speed of the neuronal signals that get sent. And then this axon, this motor unit attaches to muscle tissue at a site called the neuromuscular junction, right? So we have specific chemicals that we'll talk about in a little bit. They get passed through, basically passed through the nerve cell into the neuromuscular junction. At the neuromuscular junction, we release chemicals, and then those chemicals create a cascade of events that eventually lead to a muscular contraction. Okay? We'll take a deeper dive into each of those, I believe, in this chapter. So to start that conversation, so when the nerve cell, right, when the nerve cell attaches to a muscle, it will interact with, essentially acetylcholine will be released. It'll interact eventually with the sarcoplasmic reticulum. We remember what that stores, the SR. What's in the sarcoplasmic reticulum? Calcium, yeah, good. So it starts with calcium. Calcium is then released. One thing I want you to realize, we see this sarcoplasmic reticulum, it's around the entire muscle, right? It's all the way around. If you look all the way around, the sarcoplasmic reticulum is around the entire muscle. And then we've got T-tubules. Remember what the T-tubules do? It's basically an extension of the sarcoplasmic reticulum, but it goes into the muscle cell. Okay? So when the sarcoplasmic reticulum, let's just say it's triggered or it's turned on to release calcium, it releases calcium, and if we have a huge release of calcium in the muscle cell, calcium has a positive or negative charge? Positive charge. So if all of a sudden, if all of these, all of this sarcoplasmic reticulum, okay, let's just say if all of those just release calcium immediately on cue, what's going to happen to the polarity inside of this cell at that moment? If it's positively charged, it's going to make it a positive environment. You guys with me there? Right? We see how the sarcoplasmic reticulum and the T-tubules, they're everywhere. Right? They're everywhere. So when it's triggered to release calcium, calcium is released everywhere. And then we remember the term depolarization, right? At some certain point, that threshold's crossed and the muscles contract. Okay? So we release the calcium basically everywhere in the cell. The polarity of the cell changes and the entire muscle contracts. Why? Because we cross that threshold. Okay? We also have mitochondria in here. Remember mitochondria? What do mitochondria do? What do mitochondria do? They make something. Other things make something too, but ATP. Yeah. Remember you guys that took X-Phys with me, right? What's the answer to every question? ATP, thank you. Appreciate you guys. Good. You guys still remember that. That's good. Okay, so mitochondria, of course, other things make ATP too, but calcium and ATP are essential for muscular contraction. Okay, really important to know. We have to have calcium, we have to have ATP for muscular contractions. That's why in this image we have mitochondria, which produce ATP, powerhouse of the cell, and we're highlighting the sarcoplasmic reticulum and the T tuberose. Okay. So the next slide is going to give us a look at thick and thin filaments and how they interact with each other. We're going to start being able to apply some of this information now to the context of strength and conditioning. I'm going to actually skip this slide because I think it's easier. We just covered that. Wow, it's a lot more slides in between there than I thought. Okay, let's take a step back. We're going to skip this one. So key point, let's just recap this, make sure we're on the same page. Okay, I'm going to read this to you guys, then I'll give more context. So the discharge of an action potential from a motor nerve. So we just, a couple slides ago, we had the image of the motor nerve, right? The discharge of an action potential. So when the signal goes through that motor nerve, goes through the nodes, jumps the nodes of Rainier, goes through that axon, goes through that whole kind of like fishtail thing, right? And it attaches to the muscle cell. When the action potential from the nerve signals the release of calcium in the neuromuscular junction, right? We release acetylcholine. It eventually tells us to release calcium. When we get to that point, the sarcoplasmic reticulum releases calcium into the myofibril. That releases calcium. Calcium changes the polarity inside of the cell. That crosses a specific threshold, and then it creates tension. How does it create tension? Because everything contracts, right? So then earlier in this lecture we were talking about leverage. Now all of a sudden that muscle is pulling on something. There's tension. That makes sense? And whatever muscle that is, whether it's the bicep, it's going to create tension, and then there'll be movement. If it's the deltoid, it'll create tension and lift up the arm, etc. Okay? Cool. So sliding filament theory. Sliding filament theory is the fundamental explanation of how muscles contract. This should be probably ingrained. How many times do you guys think you've covered this in class? Up to this point, like 5? You probably, hopefully, should have this dialed, okay? But we'll go over it one more time. Basically, actin filaments at the end of the sarcomere slide inward on myosin filaments that pull the Z lines together, shortening the muscle fiber, causing a contraction. So basically the H zone disappears, the actin filaments slide together between the myosin filaments and the muscle shortens. That's essentially the thought process behind the sliding filament theory. Where now people are suggesting that there's something like a winding filament theory that they also like wrap together also. So it's not this simple like muscles are just a straight line, but they also might like contort and twist and pull. And to me, when I heard that first, I thought, oh, that's interesting, that doesn't make sense, right? But when you think about making tension, if you make tension, you guys ever like try to rinse water out of a towel and you twist it really, really tight, right? If you actually think about how much tension that creates, it's the tension that makes all the water squeeze out, right? So you think about that on the muscle level, it kind of makes sense that it might also twist and rotate too, okay? Don't need to know that for this class, but I just want to put that on your guys' radar that it's not as this binary contraction thing, but it also kind of twists and contorts inward too, okay? Okay, let's just go right to the slide and talk about it. Okay, so myosin filaments, these are our big guys. Myosin filaments, what's important to know is that this is the globular head. You guys remember what these are called? Myosin head? Think so? No? Maybe? Okay. So we have myosin filament, we have actin filaments. The Z line to Z line That is your sarcomere. Smallest contractile unit of muscle is a sarcomere. Probably should know that for your quiz, just putting that out there. What's a sarcomere? Perfect. Smallest contractile unit of muscle. Why do we need to know that? It's because this is where all the action goes down, in a sarcomere. Sarcomeres are what contract, okay? And muscle tissue, so sarcomeres are let's say a nanometer. I don't know the actual exact size of a normal human sarcomere, but they're really small. They're a nanostructure, right? But basically, you have a lot of them that stack, sarcomere, 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 all together. That creates a muscle tissue, okay? So even though we're looking at this at the micro level, this happening in 1,000, 10,000, 15,000 cells, or not even cells, but sarcomeres at a time in one muscle cell is what's causing this big systemic contraction that we can see visually or aesthetically, okay? But we got a myosin filament. Actin filaments are the small ones that slide inward, which means if a muscle contracts, let's look at this real quick. The myosin filament basically stays where it's at, right? These actin filaments are going to come together, okay? What happens to the H zone? So if the H zone is this area, does it stay there or will it disappear when a muscle contracts? Disappear, yeah? We all see that? Does that make sense? Can you cover that one more time? So this area here is the H zone. If these myosin filaments grab on to the actin and pull those inward, that makes sense, the H zone disappears. So to make sure that you're ready for questions on the CSCS exam, you're going to want to know what happens to the H zone during contraction. If you just look at it visually, it's like, well, this is relaxed, it probably disappeared. Does that make sense? Okay, so that's really the context of how you need to understand the sliding filament theory, is that the Z line and Z line are going to smash together because these myosin filaments or myosin heads are going to grab onto the actin and pull inward. So the H zone is going to disappear. Does the A band move? So the A band is myosin. Does the A band move? I see some notes. Can I get like an audible no? We good? No, it does not move, right? But what about the I band? Would the I band shrink or change? It would change, okay? So when you're thinking about studying for the CSCS, that's what you need to understand, is what's happening to these specific things within the muscle when a muscle contracts, okay? Relax, contract. Relax, contract, okay? Good? Question? Okay. So, let's break something down real quick. What would be a good analogy? Okay, so we're gonna play tug of war, okay? We're gonna play tug of war, but we're not actually gonna play tug of war, but we're gonna bet on which slide has the capability to produce the most force. So, what I mean by that is, I want you to imagine each one of these heads are a person. Each one of those myosin heads are a person, and your goal is to play tug of war on the actin tissue. You guys with me? We visualizing this? I made that clear enough? Okay. Right now, we have maybe 1, 2, 3, like 4-ish people that could grab onto that and create tension, right? So from a force production perspective, right, relative, if all of these could grab on, right, more people in tug of war is just going to be better result, right, more force. So in this specific position, do we have an opportunity to produce a lot of force? That makes sense? Relatively no, right? We can't, because there's not a lot of places to grab and pull. Whereas, if we're here, do we have a pretty good opportunity to produce force? Better than before, for sure, right? But let's go one step further. How about here? Do we have a good opportunity to produce force? You'd think yes, but we actually can't really move that much more, but our ability to create an isometric force or to maintain something is going to be really high in this position. That makes sense? So have you guys heard that there are specific ranges of motion during a movement that we produce more and less force? Right? Certain parts of a movement we can produce more force or less force. From an exercise physiology perspective, one way that we can explain that is how many of our myosin heads can bind to actin. Does that make sense? So why can we produce more force in some situations? Is because we have more opportunity to grab and pull. Okay? More people playing tug of war means more force opportunity. Make sense? Questions on that? Okay. So the sliding filament theory, there's going to be multiple phases of a muscular contraction. Basically, you have the resting phase, so we can consider you guys are resting right now. The excitation, contraction, coupling phase. What does that mean? Think about that like the pre-contraction phase. This is basically when we think about excited, something gets excited, the muscle cell gets excited. What part of this lecture does that take you back to? Make sense? What thing would cause excitement or cause a charge or a polarity change in the cell? Can we say that the nerve activating the tissue, activating the cell, starting to release calcium, right? Excitation, contraction, coupling phase, does that make sense? The innervation of the nerve has been sent. It is now, we're getting hyped to contract. Then when we reach that threshold, the contraction occurs, right? When we reach that polarity threshold, the contraction occurs. Immediately after that, we have to recharge, right? Why? Because we need to probably be able to contract that tissue again. So as soon as that threshold passes, we need to repolarize and move the calcium back out, right? Repolarize the cell, get the polarity back near a homeostatic state, or at least back to a state where the muscle is not contracted. Relax, and then we can rinse and repeat. Does that make sense? Okay, so we go through different phases with specific phase markers. So quick review, key point of those. Okay? The number of cross bridges that are formed between actin and myosin at any point dictates the force production of muscle. We feel like we have that dialed. Pretty good with that? Cover that? And we see why? Yeah? No? Okay. I can tell those of you that were in my exercise class, you're like, yep. Good. Just a heads up, if I give you guys those of you that have that in class, when we get to stuff like this, I just want to make sure we're on the same page. I'll ask you thumbs up or thumbs down. Just a really easy screen. If you guys all give a thumbs up, we're going to move on. If we have any thumbs down, no one gets left behind, so we'll just cover it one more time. Cool? Okay. All right, and then calcium and ATP are necessary for cross-bridge cycling with actin and myosin filaments. Okay? We need ATP. We need calcium. Those things together with actin, myosin, tropomyosin, troponin, etc., allows us an opportunity to contract muscle. Okay? I think we'll get a little bit deeper now, and we'll be able to start actually talking about these things in depth. I've been doing my best to use really generic terms and not talking about kind of like the deeper phase stuff so far, keeping it really high level. I think we're going to be able to start taking a little bit of a deeper dive now. So when a muscle is activated, okay, so when the muscle is activated, action potential at the nerve terminal causes the release of acetylcholine. So acetylcholine is a chemical, basically within nerve cells, that is like a messenger. Okay? Acetylcholine really is a messenger. And what acetylcholine can do, when enough acetylcholine is released, then an action potential is generated across the sarcolemma. Right? When that action potential is generated, the calcium gets released, the polarity changes, and the muscle can contract. Okay? So, the extent to which a muscle is controlled, we kind of talked about this a little bit earlier, is dependent upon the number of muscle fibers inside of that motor unit, or inside of that motor unit, okay? So muscles that function with great precision, think like your eyes, may have as few as one muscle fiber per motor neuron. One neuron, one fiber. Why? We need really fine motor skills. Again, imagine you were responsible for eye movements, really fine tracking movements, but you only had one motor unit that you could use to look up, down, right, and left. That's it. That's all you could do. One motor unit for each. You'd be like static, probably be dizzy, etc., right? Whereas we have probably hundreds of motor units, and each of those motor units maybe only activate or innervate one motor muscle cell, so that way we have really fine motor control of the movement. That way we can have coordinated, silky smooth movements. Okay? However, muscles that require less precision, think of something like thigh extension, something that we might need to be more forceful, may have several hundred fibers served by one motor neuron. Okay? So this kind of brings us to the all or none principle. Bottom line, what you need to know, the all or none principle, is that when a nerve cell activates a muscle cell, it changes the polarity within the cell. When that polarity hits a threshold, the muscle contracts. Okay? If we don't reach that threshold, does the muscle contract? No. So that's the none part. If the threshold, if we go above the threshold, does all of the muscle cells in that are innervated by that motor unit contract? They do. Does that make sense? So all or none, it's like a threshold, the threshold value. Basically, all the muscle fibers in the motor unit contract and develop force at the same time, all together or none at all. All together or none at all. Okay? So there's no evidence that a motor neuron stimulus causes only some of the fibers to contract. Basically, if the motor unit says fire, the muscles follow. If the motor unit does not say fire, they don't fire. Okay? The last piece of this implies that if we send a really strong action potential to a motor unit, if we go like exponentially above that threshold, that polarity threshold that causes the contraction, does that cause a greater muscular contraction? The answer is no, it doesn't, because it's all or none. Does that make sense? All or none. So stronger action potentials don't equal greater force. Okay. So when a muscle unit is stimulated, switch kind of back and forth here, but when a motor unit is stimulated and it activates a muscle, we see that result in basically 4 ways. One, A, is a twitch. So just one quick twitch firing. Okay, so you guys probably had a twitch before, something like that. That's just basically that motor unit, there's a single twitch. B, force resulting from a summation of 2 twitches. So we actually begin to produce a little bit of force from a summation, right? A summation of 2, basically 2, how would I say? Just 2 stimulations in a way. 2 stimulations, it accumulates force overall. Okay? Then we have unfused tetanus. Might be botching the pronunciation of that, but see unfused tetanus. Okay? Unfused. Why does it mean unfused? Is that we're kind of in control, we're regulating in a way. We're regulating the force output. We are directly interacting with the motor unit feedback, and we're getting feedback from the force that we're putting out, and we're able to adjust that in real time, if that makes sense. Okay? Something called the catch principle, or motor unit recruitment frequency. But really what you need to know is that we're able to regulate, whereas in contrast, fused tetanus is just all muscles, all go, all contraction, full force. Does that make sense? So twitch, summation of twitches, controlled contraction, maximal contraction. Does that make sense? Okay. So muscle fiber types. First and foremost, for those of you that took ex-phys with me, hopefully we realize that anytime we say something like this, is it possible that there's more than muscle fiber types? Absolutely, right? It even depends on how do we say what is type 1. Is it the contents? Is it the actual genetic molecules within it, etc., right? There's a lot of different ways to break down muscle fiber types. The easiest way is to generalize into 3 groups. Type 1 is slow twitch, okay? So give me a sport. So if we did genetic testing, of, let's say, 12-year-olds, and an athlete is 80% type 1. What type of sport could they excel at? Cross country, thank you. Endurance, bottom line, endurance, right? Do they have an opportunity to be really good endurance individual? They definitely do, right? Whereas in type 2A, fast twitch, type 2A really is like your glycolytic-like fiber types, right? They're kind of your intermediate speed, intermediate force, but also have a decent amount of endurance. Okay, I think the easiest way for me to think type 2A is like maybe soccer. Yes, there is some endurance involved, but there's also some higher force output activation stuff involved too, right? Don't get me wrong, I'm not saying soccer players are 100% type 2A, right? But that fiber type is really your intermediate, somewhat fast, somewhat endurance fiber type. And then type 2X is your high force producing, but also highly fatigable fiber type as well, okay? So we can basically put muscle phenotypes, even though there's a lot more than just type 1, type 2A, type 2X, we can still kind of group them in those 3 general categories. That makes sense, okay? So with that, I'm not gonna go through this in depth, but the bottom line of what this is getting to is what are the characteristics of a slow twitch fiber versus a intermediate fiber versus a fast twitch fiber. So to break these down, motor neuron size is kind of a predictor of the muscle fiber type. So if there's a really small motor neuron, it's probably a type 1 fiber. Okay? If it's a really large motor neuron, it's probably a type 2X fiber. Okay? Type 1 fibers have a low recruitment threshold. What does that mean? They're really easy to innervate. Doesn't take a lot of oomph to get them to innervate. Whereas in a type 2X fiber, right, we know that in certain movements, type 2X fibers only get recruited during really explosive movements or really heavy lifts, right? That's kind of a lot of effort. Does that make sense? That's a big threshold to even get those muscles to activate or to contract. Okay? We have nerve conduction velocity and contraction speed, relaxation speed. I think these kind of become a bit intuitive. I think the key ones to point out are that endurance. Which cells or which muscle fiber types have the best endurance? It's going to be type 1. What has the worst? 2X. In contrast, for force, what muscle fiber cells or muscle fiber types have the best ability to produce force? Type 2X, along the continuum to type 1. You guys with me there? So again, I don't want to spend time going through each of these individually, but I do think for just CSCS and study prep, just read through them and just think about it contextually about like, does this make sense? And you'll find yourself realizing like, oh yeah, that totally makes sense. That fiber type, based on its characteristics, would act that way. So when you get an exam question that says something like, what fiber type can produce the most force, it becomes really intuitive and you can answer it that way. Okay? Let's see. Okay. We kind of already covered this, but muscle fibers are innervated by specific motor units. Motor units are composed of fibers with specific morphological and physiological characteristics that determine their functional capacity. In other words, what that means is that a motor unit kind of has a specific purpose. Some motor units might be responsible for something like endurance. This is a generalization, but does that make sense? Motor units kind of band together muscle cells and tissue that function a specific way, which if you think about it, if you're responsible for our physiological function, right? Like think about if you're responsible for a company, you're a CEO of a company, and you have a specific task that you need to complete, right? Does it make sense to go and you know that there's a timeline on this task? Are you gonna go to your person that you know is super methodical and slow and has really great endurance, or do you need to go to the person that's gonna be quick and fire and get the result right away? Does that make sense? So think about it from like a brain control perspective. It makes sense that we have motor units that are responsible for certain, let's say, physiological phenomenon. Does that make sense? And then we can kind of go to those and recruit those to get specific things accomplished, or their functional capacity, so to say. Okay. So motor unit recruitment patterns during exercise. So force output. Now we're getting kind of starting to translate into strength and conditioning. Force is mass times acceleration, right? How do we change force output? So let's say we're doing a bench press. How do we increase force strictly from a physiological perspective of the content that we've covered? We kind of have two options. We can either recruit all the motor units that we have. Does that make sense? So we can recruit, if we recruit all motor units, if every helper we have contributes a little bit of force, is that going to result in our largest force output capability? Does that make sense? If we could find a way to activate every single muscle that can push, then we will produce, in theory, near the max amount of force that we can. But does it function that way? No, right? We don't always recruit every fiber that we have in our body that can do that. Why? Because we kind of revolve through motor unit activation. But what we need to know is that we can either change the number of activated motor units, that's going to result in increased force, or how frequently we activate the motor units. Okay, so earlier we talked about something called the catch principle. Really small variations in the frequency of motor unit activation have significant changes in the force output that is expressed. Okay? What I think is important to boil this all down to is that, does this sound like something that we have intuitively, or that's something that we need to learn to do? Does that make sense? What happens in the first 8 weeks of strength training? So let's say you guys have never strength trained before, and you get under a barbell and you go to start bench pressing. In the first 8 weeks, are you gonna get just like yoked? No, but you get a lot stronger, right? Like if we measure your strength and your force output over the first 8 weeks, you get stronger, right? So how do we explain that then? Is it nervous system adaptations or peripheral adaptations? So muscle or nervous system, what do we think? Nervous system adapts. And in what ways, based on this slide, would you say or think that the nervous system adapts? Put it in other words, do you think we become more coordinated in our ability to recruit more motor units in those first 8 weeks of resistance training? So, I mean, do you think we learn how to get all of these entities to work together for one outcome? Right? It's like a coordination component, right? In other words, if you don't lift heavy, are you ever going to get that response? That makes sense? Probably not really. Or move fast, at least. Okay. What I'm getting to is that this is kind of like the fundamentals of how we explain the first 8 weeks of resistance training and the adaptations that occur, because people's muscle mass doesn't like exponentially double or triple, but their bench press might go from 135 to 185 or something like that. It might be significant, but their muscle mass barely changed. So how do we explain the phenomenon? Well, they probably got more coordinated in activating more motor units at a very specific time. Make sense? I want to be able to apply this info. Okay, proprioception. I think we're getting to the end. We've got like 20 minutes left, so I think we're on track. Okay. Proprioceptors. Proprioceptors, specialized sensory receptors. They give feedback. They help us with feedback loops. These are type 3, type 4 nerve afferents. What that means is that they are nerve cells. Okay? They're basically nerves that send us information about what is happening in the muscle. For some reason, there's this thought in kind of like sport fitness that the brain controls everything outward. But what I want you guys to be aware of is that there's also gray matter, so brain matter, that is smart in places like in your low back, in your vertebral spine, that also get feedback, that send feedback back and forth to other nerves that are within the body that provide context to what's going on. Those things that give us context are proprioceptors, type 3, type 4 afferents, like muscle spindles, like Golgi tendon organs, that give us a heads up about the current status of that area, okay, of that tissue site. So, we need these to optimize our movement and how we function. Starting with muscle spindles, basically, when a muscle is stretched really, really quickly, the muscle spindles deform. Does that make sense? If you really quickly stretch a muscle spindles are inside of the muscle, it gets deformed. When it gets deformed, it activates this sensory neuron, type 3 or type 4 afferent, which sends feedback to the spinal cord, to the brain, which is an extension of your brain, which is why I started with that, okay? It doesn't have to go to the brain, it can go to your spinal system. Not have to go back to the brain, it can go right back to lumbar, something, gray matter, and go right back. Okay? Impulse to the spinal cord, where it synapses with a motor neuron, causing basically a contraction or a response. Okay? How do we use this in sports science? I'm just going to give you guys two scenarios. I'm going to jump from this position as high as I can. Am I going to jump higher if I start in this position, or if I drop and then jump? Which one will I jump higher? Drop, jump, counter movement jump, right? We've heard of the term stretch shortening cycle, right? But also, from a neuronal perspective, think about how this functions. How does a muscle spindle function? If I start here, right, and try to jump as high as I can, am I activating muscle spindles? Is there a rapid stretch, deformation of the tissue? If I start here and jump, am I rapidly stretching on the way down? No, I'm taking away that. So we call that basically like a squat jump. Okay? Whereas if I start, if I drop and jump, I can jump a lot higher. Why can I jump higher though, is the question. Looking at the slide, can you guys answer that? What am I deforming as I rapidly drop to the ground? We can just generalize to the leg. We don't have to get to like what quad muscle, whatever. But if I rapidly drop, am I stretching something? Yeah? Bottom line, yeah, right? And if I'm rapidly, so you guys are like, what is it? If I'm rapidly stretching, what is going to happen? Causing what? Excessive muscle contraction. Remember, we're talking about force output, right? The more force I put into the ground, the higher I jump. Pretty simple, right? Well, more force per time that I'm touching the foot. But if I drop and stretch muscle spindles, do I now have more motor units involved in pushing and propelling me upward than if I just stayed still? I do, right? Does that make sense? Can we translate that to things like a bench press? If you go really slow on a bench press, is it hard compared to if you drop the bar? I guess if you bounce it off your chest, of course it's easier, right? But if you go down slow and then right at the bottom you drop and press, does that make sense? Okay. Why can we do more reps with bench press at a certain load if right at the bottom you drop the bar and accelerate? Muscle spindles? Maybe? Yeah? We good? Starts in muscle and then spindles? Yeah? Yeah.
Would it need to be because you're pre-activating the muscles beforehand too?
You could predict. Yeah, you could predict, but it's reflexive. It's reflexive. So you're not here, and you're not gonna say, okay, in 2.5 seconds, I'm going to activate
No, I said preload.
preload.
Yeah.
You might be predicting that, but at the same time, it's really on impulse. It's really on your like response to contraction. If that makes sense. Yeah.
So at what speed does it not work? Like you squatted and then you paused at the bottom,
Yeah.
and you said that we all know that doesn't work as well.
Yeah.
So at what speed, if you go slowly down?
You know, that's a really good question. It's probably, I don't know the answer. I would assume per muscle it's probably different. And it's gotta be rapid and forceful. If that makes sense. It has to be a really rapid stretch. So basically, like, the fastest you can move your body will probably result in spindle activation. Yeah, I don't know what actual speed is the threshold, but like, this pausing
Doesn't work.
is very different than a massive excel. Okay. We're gonna skip that for now. Golgi tendon organ. Anybody have Akiva? You're not very flexible, right?
No.
You have shorts on?
Yeah.
Yeah, weak for me.
Oh god.
Okay, so we're gonna talk about the Golgi tendon organ. Do we remember what the GTO does? Golgi tendon organ senses what? Tension. It senses tension. So if we're gonna lift a car, we have Golgi tendon organs in our bicep. If we're gonna try to lift a car, let's say something catastrophic happens and we need to lift a car, right? And we go to lift the car and our bicep is about to tear off of the bone. Would it make sense that we have some sort of protective mechanism that said, stop contracting, just relax so we don't tear that off? Does that make sense? That's what the GTO is. Keep doing your back. You guys see Akiva okay? So they on their back? Okay, so we're gonna activate his GTO real quick. We're gonna do this and we'll talk about the GTO, okay? Can you do a straight leg raise? Keep your leg straight, don't bend your leg. Yeah, can you see that? That's maybe like 45. We're not gonna go like goniometer and measure it, but this is Akiva's mobility, okay? So GTO can sense tension, so I want you to push with your heel as hard as you can into me. Push hard, hard. I can't hear you pushing. Push.
I'm going.
Good. So we're creating tension right now. Where in his hamstring? Go ahead, relax. Good, and then we can release. You guys see how far his leg moved? What's happening? Go ahead, contract, push. As hard as you can. Push. The body's sensing tension. Remember, it's gonna think, oh my gosh, I don't wanna tear my hamstring off. Oh no, I don't wanna do that. So what do? Relax, Akiva. So you override and it allows more relaxation, increase range of motion, so that way you don't tear the tissue off. Go ahead, push. Keep pushing harder. Relax. Okay. So now we're right up to vertical, right? And then can you do a straight leg raise on your own? Is that higher than before? Yeah? Okay, thank you. So,
Stretch my elbow like that.
probably should. That was pretty bad, dude. I know. I wouldn't do a whole lot of activities without stretching.
You should have called my Michael, right?
You're a risk. You're a walking risk. Okay, so GTO, does it make a little bit more sense? Its job. So what we saw was we created tension and the body had to respond, right? It had to respond. So let's go to the first slide. They're proprioceptives and tendons near the myotendinous junction, the muscle tendon junction. They're in series with extrafusal fibers, okay, with an extremely heavy load. So I just held Akiva and I had him push as hard as he could. We can consider that a heavy load, okay? Place on the muscle. Discharge of the GTO occurs. So GTO is an afferent sending feedback to the brain saying, hey, this is too much force. This is too much. This is kind of maybe risky, so to say. The sensory neuron of the GTO activates an inhibitory interneuron in the spinal cord, which synapses with and inhibits a motor neuron serving the same muscle. In other words, reciprocal inhibition is going to kind of like allow that area to relax, to increase range of motion. I don't want to go too deep into it right now as we cover it, but do we get the gist? We activated the GTO was on, it interacted with his nervous system, sending a feedback to the brain or to the gray matter in the lower spine. that says that we need to relax. And then with that, it allows us to increase range of motion. Okay? I'm just gonna check how many we have. Wow.
You're at 43 out of 66.
What was that?
43 out of 66.
Where do you see that?
I can see it online.
Oh, that's nice. Thank you. Okay. So bottom line, how do athletes increase force? How do people improve force production? Okay. So we need to incorporate phases of training that use heavy loads to optimize motor unit recruitment. Do we understand that a little bit more with the context that we added today? We need to learn how to activate a lot of motor units at the same time to produce a lot of force. If you don't do that in your training, can we expect you to be super forceful? Probably not, right? If we increase the cross-sectional area of muscles involved in the desired activity, right? Force is equal to mass times acceleration. If we have more muscle mass involved in the process, we can probably produce more force, okay? And perform multi-muscle, multi-joint exercises that can be done with more explosive actions to optimize fast twitch recruitment. Multi-muscle, multi-joint. Give me an example of a multi-muscle, multi-joint movement. Power clean, perfect. Power clean, okay? Loaded vertical jump, etc. Things that are powerful and fast. Why is that valuable? Because it's going to require you to activate motor units quickly and forcefully and get better at your synchronization of relaxing your antagonists while you activate the agonists. Okay? Okay, so the heart, let's do this real quick. Okay, I'm pretty sure this is, when I took the CSCS, that was in 2016? 2016? There was a question, explain the flow of the heart, okay? Explain the flow of the heart, explain the flow of the heart. Explain the flow of blood through the heart. So let's do that really quick. When blood comes back to the heart after being pumped. Whoa, Siri. When the blood comes back to the heart, where does it start? What is the big vein that it comes back into? Thank you. Okay, and then that goes into what thing? Is this an atrium or a ventricle, or what is this? Atrium, is that the right or left? Okay, and then it goes through what valve? Tricuspid valve into ventricle, and then from there, where does it go? Does it go this way? Answers, yes, you guys can be confident. Yeah, let's try and trick you. It sounds like it worked. Okay, good. So then it comes up here, okay? From here, where does this blood then go? To the lungs, right? Why? To get oxygenated, so we can drop oxygen off at our working tissue. After it comes back from the lungs, where does it end up? Left atrium, thank you. From the left atrium, it goes through what valve? Mitral valve into left ventricle. From the left ventricle, it gets ejected to everywhere else. Back through the body. And we rinse and repeat. Okay? Quick heads up on the exam, that might be something like vena cava, atrium, ventricle, etc. Just be familiar with that flow, okay? I don't think we need to go over that as a group. That's more of something you just need to kind of be aware of. Honestly, at this point in your academic career, probably will come just through intuition, okay? Skip these. What is the normal rhythm of the SA node? How many beats per minute? 100? 60? 60? Okay. Bottom line, what we need to know is, let's be familiar with these terms. Bradycardia, less than 60 beats per minute. Tachycardia, greater than 100 beats per minute. Okay, so make sure we have those terms down. bradycardia, tachycardia. Almost out of time, so I want to flow through this. EKG, are you guys familiar with PQRS? What does the P wave represent? What's getting depolarized? Think flow of the heart. Think flow of the heart. Where's the blood right now in the first place? Atrium? Right or left? Right. Boom, boom. Got these? You guys good? Is this review or is this, we need to go over this? Is this review? Okay, well, let's see, I want to respect you guys' time and not go late. So we'll go through it next class in the beginning. We'll bring back if we need to. Okay, if we need to, we'll go back over this. Okay, PQRS honestly should be pretty simple. Just know that every one of those waves is associated with the depolarization of an atrium or a ventricle. The blood's getting ejected from one place, going to the next. Ejected from one place, going somewhere else, and then rinsing and repeating over and over again. Okay? This is... Okay, getting into pulmonary fizz. Let's stop here. Yeah, we'll stop here. Distribution of blood. I'll try to remember this slide. We'll stop here. We'll pick up here next class. For the quiz will be on the whole chapter. That quiz isn't due until midnight that night, so we can pretty quickly cover this. But still, read ahead. Okay, this is still review stuff, so we should be able to get through all of this, but I don't want to rush it and skip things in the beginning. Okay, so I'll see you guys on Tuesday. We'll finish this up, and then we'll get into chapter 2, biomechanics. Cool? All right, Sparky.